right, hello everyone. So we are looking at lesson 6 now, probability distribution. First question here is review from lesson 5. So we're just talking again about expected value. The things that you're going to have to do here are actually not too bad. Just a lot of number crunching and perhaps a little bit more writing than you would like. But I don't think that you're going to find the ideas to be too bad. So let's just hopefully get through this video quickly. So this first paragraph here that you can see is just talking again about the expected value, what we talked about in lesson 5. Remember that it is like a long run average. If you have various things that could happen and you have the probability associated with those things, then you could find kind of again an average or an expected value from those. So you can see in question 1, it says, suppose a cancer charity in a large city wanted to obtain donations to send children with cancer to a circus appearing in the city. Volunteers were asked to call residents from the city's telephone book and to request a donation. Volunteers would try each phone number twice at different times each day. If there's no answer, then a donation of $0 is recorded. Residents who declined to donate were also, of course, recorded as a 0. The table below shows the results of the donation drive. So you can see the various amounts of money that people donated, and after all was said and done, the probability that calling somebody would result in each of those given amounts. So just like in the last section again, should be getting pretty good at this. If I wanted to find the expected value of the amount donated, I would simply multiply, of course, all of the donation amounts times the probability of those amounts. And again, this is what I'm also kind of talking about here with the not too difficult of a concept, but a lot of writing. Okay, but I would multiply and add those all up together, and I'm obviously not going to do that here for you on the video, but that would result, if you did do it, in 27.5, which of course, since we're talking money, would be $27.50. Now, is any one person going to give $27.50? Probably not, but in the long run average, I would expect to obtain about $27.50 from any one person that I called. Because again, you've got people giving $100, you've got people giving $0, but they have various probabilities of those things happening. So that's how we would interpret this expected value. So now we are moving into, we could, with the problems that we're about to do the same thing, find the expected value. But the big thing for this section is that we are going to make our own probability tables from information that we are given. So we've been lucky enough that we just have it there for us, but what if we didn't? What if we had to create those ourselves? So we're going to look at a few examples now of doing that. So the first thing you need to recall from Math 2, I know that was a long time ago, is that if you have two independent events, and think about what that means. Independent events means they don't, the thing that happens in one event doesn't interfere with the thing that would happen in another event. So let's say we have events A and events B. If we want to talk about the probability of both events occurring, then what we would do is take the probability of A and the probability of B happening, and we would multiply them together. So that's a multiplication rule that we talk about with independent events. Again, independent events means that these two events have nothing to do with each other. The outcome of this event does not affect the outcome of this event. All right, so you're just going to need to remember that in order to make these tables here. So, of course, an example always makes things better. So let's look at an example. About 11% of adult Americans are left-handed. Suppose that 2 people are randomly selected from this population. Create a discrete probability distribution for the number of left-handed people in a sample of 2 randomly selected adult Americans. Okay, the key here is to be organized. So we need to, first of all, maybe make a table of the possibilities. Oh, goodness, that happens every time. The possibilities of person 1 and person 2, what they are. And then, of course, the probability of those things happening. This is going to be the first thing that we do in these situations. Okay, so this is where, again, it pays to be organized. Person 1 could be left-handed. Person 2 could also be left-handed. That's one thing that could happen. Person 1 could be left-handed, but person 2 could be right-handed. That's another thing that could happen. We could have right-handed and left-handed, or we could have both right-handed. These are all of the combinations. If I pick 2 people out, this is what I could get. Okay, so the hard thing here is just to make sure that you have all of the combinations, all the possibilities of things that could happen. Now, how do I get this probability? Well, let's remember, we're told that 11% of the population is left-handed. So that, of course, would imply that 89% of the population is right-handed. Okay, so we might have to do this part ourselves, but I think we can do that. 11% is left-handed, then 89% is right-handed. So going back to this table, if this person here that's left-handed, there was a 0.11 or an 11% chance of that happening, and there was an 11% chance of this happening, then and again, going back to this, the probability that both of them are left-handed would simply be 11% times 11%, 0.11 times 0.11, which is 0.0121. So that's how I would come up with that. The next one, if person 1, there was an 11% chance they were left-handed, but person 2, there was an 89% chance that they were right-handed. So the probability that this happened and this happened would be 0.11 times 0.89, and I would get this number. Okay, I'm going to continue to do that on down the line with those associated probabilities. Of course, this last one we would expect to be pretty darn high, both of them right-handed. That seems like the likely thing to happen. But I'm just going to multiply those probabilities out, and you can see this is 79% chance right down here. And so I've collected this information, which is great. I need to make it look more like these tables that we have here, because I've got a couple of things that go together. So in order to complete this, my table should look like this. Remember, it says a discrete probability distribution for the number of left-handed people. This doesn't really tell me the number of left-handed people easily. So I'm going to make this table a little clearer. I'm going to say the number of left-handed people. If I'm sampling 2 people, then I've only got the options of none of them are left-handed, 1 of them is left-handed, or 2 of them is left-handed. So those are my options there. And I'm going to use this information over here to fill this out. The probability that 0 of them are left-handed, well, 0 of them are left-handed, that's right here, where they're both right-handed. That has a probability of 0.7921. 1 of them is left-handed. Now this is a little tricky because I actually have 2 scenarios here and here where only 1 person is left-handed. So what do I do with these 2 associated probabilities? Well, I would add them up. Oh, this is supposed to have a 0. Sorry, it's supposed to be the same as that one, of course, because it's both 0.11 times 0.89. So I would add these up. I have this probability and also this probability. These are both scenarios where there's 1 left-handed person. So add these up, and I would get 0.1958. It's the probability of 1 person, and then both left-handed, of course, is that one situation over there that we started with. So this is what my discrete probability distribution would look like, and I made it myself, which is great because I had that information. All right, so we can answer questions all day long about this. What is the probability that at least 1 person is left-handed? I don't know why that says is left-handed. It's supposed to say that. What is the probability that at least 1 person is left-handed? Well, I would just look at my table easily enough. At least 1 person means 1 person or more. So the probability that 1 person is again 0.1958. The probability of 2 people is 0.0121. And of course, I would just add those probabilities up to get the total probability of at least 1 person. If I did that, I get 0.2079, which of course is 20.79%. So if I take 2 randomly selected people, I would expect that there's a 20% chance, a little over 20% chance, that at least 1 of them is left-handed. Not a great percent chance, not a great probability there, but that's how I would interpret this. Now, I could also interpret this with an expected value. I could say, what's the expected number of left-handed people? And you would do that just like we started today's video. You would multiply these numbers with the probabilities and find that out. I don't know that that's very meaningful in this situation. All right, let's take a look at another example. Suppose that on a particular island, 60% of the eggs of a certain type of bird are female. You spot a nest of this bird and find 3 eggs. You're interested in the number of male eggs. Assume the gender of each egg is independent of the other eggs in the nest. Create a discrete probability distribution for the number of eggs in the nest. Now, a couple of things. Maybe make a note for yourself. Female, it looks like they're 60% of the eggs are female. So that would mean that as far as males go, we would expect 40%. Okay, so that's just some upfront information you need. Next thing you need to do, and this is a little bit annoying, is you gotta now make a list. You've got 3 different eggs. And you need to write down all the possibilities of male versus female of 3 different eggs now, and then find their probability. Now, to save time on this video, so you're not just watching me write down letters and numbers, I'm going to, just like in a cooking show, I'm going to show you it already done so we can look at this easier. So notice the first thing I did was make a list. Female, 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 male. I went through all of them, all of the different possibilities. And then I multiplied for the first one, 60% times 60% times 60%. That's where this number right here came from. This was 60 times 60 times 40, and so on. Of course, I have some repetition in my numbers because there are multiple ways that I could get 2 females and a male, for instance. 2 females and a male could come like this: female, female, male, female, male, female, male, female, female. So I kind of have these little dashes next to the ones that are alike there, just to point that out, that there are going to be some repetition in numbers. Once I have all of this written out, and again, I realize it takes some time, I do need to make my actual distribution here, my probability distribution. Question is asking about number of male eggs. If I have a nest that holds 3 eggs, I would have the possibility of there being no males, 1 male, 2 male, or all 3 males. Where did these numbers come from? Well, I just looked over here and I said, where is there 0 males? That first one, that's the only one. So that's the probability. 1 male, so I went and I said, where is there 1 male? Here, and then I've got another one here, this 0.144, and then I've got another one here, this 0.144, and I just added those up. That's where that number came from. 2 males, add up all the times when I had 2 males. And then 3 males, that should only be 1 time. All 3 males was 0.064. So that is where that came from. And now that I have this table, again, I can answer all sorts of questions. The one question that was asked of me here, what is the probability that no more than 2 eggs are male? So no more than 2. What does that mean? That means I can have 0, I can have 1, and I can have 2, but I can't have any more than that. So notice that I added up the probabilities of 0, 1, and 2, and I got a very large probability of 93.6%. All right, one more example. In the 21st century, about 3% of mothers give birth to twins. Suppose 3 mothers-to-be are chosen at random. Create a discrete probability distribution for the number of sets of twins born from the sample. So again, some upfront information. Twin probability is 3%. So no twin probability is quite large, 97%. So those are the percents that I'm working with. The next thing you would need to do is set up a table. Mom 1, mom 2, mom 3, and the probability. And a lot like the egg problem from a second ago, you're going to have quite a few examples here, quite a few probabilities, because you have 3 different things you have to go between. So you could have twin, 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 no twin, no twin. And in fact, once more, I'm just going to show you my completed table. So here's what I did. I get very systematically, made sure that I had all of the different types of things that could happen. These probabilities, they're pretty small because I'm dealing with 3% for a lot of these. 3% is very small. So these numbers are kind of annoying to work with because they're so small. But again, once I have that, remember I'm just multiplying 3% times 3% times 3%, 3 times 3% times 3% times 97%. And remember when you multiply percents, you got to move that decimal over. So it's really 0.03 times 0.03 times 0.97. That's where that came from. And then again, to complete it, I have to make the actual table of number of moms who have twins and the associated probability. So again, I've got 0, 1, 2, and 3 is the number possible of twins. And then I just go through my table. 0 twins, of course, that's down here. No, no, no. So that's the largest probability, as you might imagine. 1 twin, go through and find all of the places that have one twin in them and add up all of those probabilities in 2 and 3 and so on. And so then, of course, again, after you have that table, you can answer questions like this. What is the probability that at least one of the 3 mothers did not give birth to twins? That's kind of a confusing question. At least one did not give birth to twins. And so for that, of course, you would expect that to be pretty high. So if we did that, if we're looking for that, I just took 100% and took away this probability of 3 of them having twins, which is very, very small, obviously very small probability that all 3 of them would have given birth to twins. So I took that small percentage away. And that led me to about 99%. So there's a 99% probability that at least one of the 3 mothers did not have twins. So I took away the probability of all 3 of them being twins. And that's that. Again, I think you guys can handle answering these questions. It's really just going to be the writing of the possibilities with the associated probabilities. It's going to take some time. All right, we will practice this in class, and I will see you there.